All right, good evening, boys and girls, children of all ages watching this calculus video. We are today going to look at what's called the mean value theorem. We're going to look at some stuff that comes from it, and we're going to look at a very new word for us, a very, very important word as we get into this quarter two. But I'm going to leave that hanging, get there till leave it hanging until we get there. All right, so we're going to look at the mean value theorem in its context to derivatives. And this very wordy theorem, as it always kind of is, if y is equal to f of x is continuous at every point of the closed interval a to b and differentiable at every point, so notice we have that differentiable piece, of its interior, then there is at least one point on this interval at which this statement is true. And this is basically saying, over here on the right, you'll notice this basically saying the tangent is parallel to some chord or some secant line on the function. So if we had some sort of, I gotta get my pen, don't I? Oops. All right, so this is basically saying if I had some function, we can deal with quadratics pretty easy, and we say that this is a closed interval from A to B, we could say there's some point on this line. So here's that chord, here's that secant line, really. There is some point for C, some x value C that's on this line that would create a tangent that's parallel to that chord or to that secant line. And it guarantees this. The mean value theorem guarantees this for us. And it's actually kind of important as we get moving through here. Okay, so what we can kind of do with this is we can show that x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Well, we know this function is continuous and it's differentiable on the function from 0 to 2, or on the domain from 0 to 2. Now what we can just kind of look at is what this looks like graphically. Okay, so we have our xy axes, we have at 0, 0, and beautiful quadratic here at 2, 4, and the point 0, 0. And we basically want to see if this if this is still true. Is there some point on here? Can we find some point x which makes a parallel tangent to the secant line between 0, 0 and 2, 4? Now, because of the mean value theorem, it actually does guarantee it, because we know the function x squared is differentiable between these 2 points and it's continuous between these 2 points, and therefore we're good. We should have one. So I basically want to do f of, what am I doing here? F of 2 minus f of 0 all over 2 minus 0. And I know this to be f of 2 is 4 minus 0 over 2 minus 0, which is 4 over 2, which is 2. And I'm basically saying, okay, where the derivative is 2x. So is there some value that makes 2x equal to 2? Well, of course there is. X is equal to 1. So if we looked at this line, that's ugly. Let's go undo on that one. If we made some line here, my secant line, at x equals 1, we'll pretend 1's right in here somewhere. This is not a very good graph. It's not one of my best. Whoa, what's going on here? Okay. There is a tangent line at x equals 1 that's parallel to the secant line between 0, 0 and 2, 4. Okay, so that's what the mean value theorem tells us. There's some things they're going to be asking of you in the textbook. They're actually going to be asking you this basic question. Can you show that there is a point on here that shows that satisfies the mean value theorem? All right. So what we kind of lead into here on this particular section is some increasing and decreasing things, some things that come from it, how we can use the derivatives to determine increasing and decreasing, and again, that big word that we're getting to. Okay, so what I'm going to kind of say here is we kind of know what it means to be increasing and decreasing. We did this a lot last year, and really this is just saying between two x values, if it's increasing, the y values are increasing, and we kind of know that. And they actually, in the textbook here, we're actually naming this as a theorem, or actually a definition. And then there's some corollaries that come from the definition. Corollary is just meaning something that's nice that happens when we get this definition. All right, so the first corollary here is for derivatives. If we can let f be continuous on some closed interval and differentiable on some open interval, just like the mean value theorem. And we actually kind of know this already. If the derivative is positive, that means the original function was increasing because the slope was positive, right? So this is what this means. The derivative is positive, so the slope is positive and therefore increasing. And likewise, we can say if the derivative is less than 0 at each point, then it's decreasing on the interval. And again, we've discussed this in length already, and I'm pretty sure we kind of know this as fact. So a couple other things that happen here is again, this is kind of something we know, but they're kind of putting it all together to help us into this next chapter. And the first thing here is if the derivative is 0, then we know that the original function was a constant function. So we're going to use this big C, and this big C shows up a lot in the next couple chapters here. Okay, so big C being constant value. So if we take a derivative of a constant number, the derivative is 0, which means the slope at all points is 0. And the second piece here, this is really kind of our big one. If we have two functions, the derivative of f and the derivative of g, if we say they're equal, then there is some constant such that f of x is equal to g of x plus c. They're probably not, the original functions are probably not the same original functions, but there are multiple functions that have the same derivative. Let's just think about one. If I just think about really simply, I can think about 2x plus 4 and 2x minus 7. The derivatives are the same, but the original functions are different. And that's kind of interesting for us because what we're going to be doing is we're going to be given f of f prime and g prime, and we're going to be finding the original f and the original g that those derivatives came from. And you notice that f of x and g of x are not the same function, and they actually differ by a constant value. Okay, so f of x is this. We could say g of x is just plus some value to get f of x. I think it's plus 11 if I'm doing my math correct there. All right, so this actually brings us to this big word. I've kind of hinted at this word a little bit. This is the antiderivative. So we've been finding a lot of derivatives. So what we want to do now is eventually start looking at the antiderivative. This is going in the reverse direction, finding the function given the derivative. Usually we've been finding the derivative given the function. Hopefully my battery holds up here. All right, so the antiderivative, a function f of x is an antiderivative of the function f if the derivative of f of x is the little f of x. So basically saying if I had 2 as a derivative, I could say my original function might have been 2x plus 4 like before. So f of x, 2x plus 4 is the antiderivative of 2 because the derivative of 2x plus 4 is 2. Now you might understand, you might be thinking, oh, well, what if it was plus 6? Well, it's the same thing, and that's one of the things that we're going to need to be able to figure out is what was that constant term, all right? The process that we're going to be finding, just like we had the word differentiation when we found derivatives, now we have antidifferentiation. Okay, so that's what the word we're going to be using. It's a really long word there, but that's how we're going to be referring to this process. So one of the things that we could ask is, hey, what would be a function whose derivative is sine of x? Basically saying, hey, what's the antiderivative of sine of x? And it can't be cosine of x because the derivative of cosine is negative sine. So I could actually say it would be negative cosine of x. But the problem is it could have a constant out here. So this is actually how we write it. We say, okay, the antiderivative of sine of x is negative cosine of x plus c. But we could say, hey, what if it goes through the point 0.02? The antiderivative goes through the point 0.02, which means now I can say negative cosine of x plus c equals, actually I need to delete that. I need to delete the x because I'm actually going to plug in x equals 0. And I'm going to let that equal to 2. Well, cosine of 0 is 1, but it's negative, so it's negative 1, plus c is 2, and it gives me c is 3. Well, this is super, super nice for us because that means the original function, the derivative or the antiderivative of sine of x that goes through the point 0.2 is actually the function, let's call it f of x, or actually let's not do that. Let's call it big f of x, like the definition was, is negative cosine of x plus 3. So the original function, the antiderivative was negative cosine of x plus 3. And this is super, super cool for us. We're getting really, really starting to get deep into the calculus, getting out of derivatives, and thinking about how to go in the reverse direction and find the antiderivative. Now, there's a lot of different things we could be doing with this. We could find velocity given acceleration. We could find position given velocity rather than going in the other direction, rather than going in the derivative direction. And I'm going to kind of leave it there. I'm going to leave a lot of the work to us tomorrow in our class. And you have your assignment sheet. I believe I gave you enough information. If I didn't, you got to let me know tomorrow, and we can go from there. Hope you have a good evening, and I hope the math serves you well.